Welcome to this video, which is about risk assessment and acceptance of CO2-based fuel for road traffic and aviation. My name is Linda Engelmann and I work at the Chair of Communication Science at RWTH Aachen University. This video is part of a 3-video series recorded for the eCOCO2 project, a Horizon 2020 project that focuses on the direct electrocatalytic conversion of CO2 into chemical energy carriers. Before we get started, let me show you the contents of this video. First, I'm going to talk about why it is important to study acceptance of CO2-based jet fuel. Second, I'll tell you a bit more about factors that can influence acceptance of CO2-based fuel, namely affective evaluation and cognitive evaluation. Finally, we'll have a look at the acceptance of CO2-based fuel and about the connection between acceptance and the perceived harmfulness of CO2-based fuels. Let's start with the first question. Why do we study technology acceptance of CO2-based fuel? Results from previous studies indicate that carbon capture and utilization technologies are viewed as delaying the actual release of CO2. At the same time, respondents in these previous studies felt that CCU technologies create jobs and useful products. Also, they felt that CCU represents a step in the right direction to combat climate change. Apart from these benefits and barriers that people may perceive for an innovation such as CCU, risk perceptions may impact the acceptance of an innovation. As they are a potential impact factor, we have to study them as early as possible. In previous research, the fear of toxicity and potentially harmful consequences of handling a product were identified as a risk perception. In acceptance research, different acceptance models exist that try to model which factors influence if someone in the end accepts a technology or a product or not. The diagram you see here is based on a model by Hütz et al. From 2012. Besides other influencing factors in the model, such as a person's moral norms, attitude and acceptance are impacted by cognitive evaluations. These are, for example, perceived risks, costs, or also perceived benefits. Apart from that, affect has an influence. That means positive or negative feelings towards the object. In this model, both affective and cognitive evaluation have an indirect influence on acceptance, as they influence attitude, which has an impact on the intention to accept, and finally on acceptance. Studies show that when these cognitions and affect are, for example, both positive, their contribution is equally high. But when, for example, cognitions are positive and affect is negative, feelings tend to dominate over cognitions in the formation of attitudes. Let's have a closer look at the affective evaluation of CO2-based fuel. As already mentioned, the affect a person can feel towards an object can either be positive or negative. According to technology acceptance theory, affective evaluations may impact a person's acceptance towards a technology or a product, such as CO2-based fuel. But how do we measure something like an affective evaluation? One way to investigate people's affective evaluation is to ask them to fill in a semantic differential. A semantic differential can be used in surveys. It depicts pairs of opposites that allows participants to indicate how they feel towards an object. In a study on people's risk assessment regarding the perceived toxicity of CO2-based fuel, we questioned 138 laypeople on their affective evaluation. This was done separately for conventional fuels and for CO2-based fuels. The opposite pairs that were used for semantic differentials were risky and safe, dangerous and harmless, polluting and eco-friendly, toxic and non-toxic, dirty and clean, as well as harmful and not harmful. The figure you see here shows a comparison of the mean values for each of these pairs over the whole surveyed group of people. The results for conventional fuels are depicted in black, while the results for CO2-based fuels are shown in gray. A slim gray line between the scale points 5 and 6 indicate the middle of the scale between the extremes. We found that the CO2-based fuel was perceived to be safe, less dangerous, less polluting, less toxic, cleaner and less harmful than the conventional fuel. While the results for conventional fuel in black lean towards the left side of the scale, that means to the more negatively coded part, the mean results for CO2-based fuel are close to the midpoint of the scale. This indicates a rather neutral, effective evaluation of CO2-based fuel. Let's move on then to the cognitive evaluation of CO2-based fuel. The cognitive evaluation of a technology or product can include, for example, perceived costs, risks, or also benefits. The focus in this study lies on perceived harmfulness. Therefore, we focused for now on perceived risks. As depicted in the model you just saw, cognitive assessments such as risk perception are a potential factor that influences acceptance of a technology or product. These risk perceptions can be focused on different entities. It is possible to fear risks of a product or technology for different so-called risk targets. This can be, for example, for oneself, one's children, but also for animal life, plants, or the climate in general. On this slide, you see one way to measure these risk perceptions. In the survey, people were asked if they perceived negative consequences for different risk targets by CO2-based fuels compared to conventional fuels. On a scale from strongly disagree to strongly agree, people then indicated how much they think that CO2-based fuels pose a risk for their health, the health of their children, or children in general, etc. Let's have a look at the results. The figure on this slide shows the mean agreement over the whole sample of 138 laypeople for each of the included risk targets. We can interpret them as follows. For example, for the climate, people rather did not perceive that CO2-based fuels have a negative impact on the climate in comparison to conventional fuel, as the mean for the risk targets is 2.71 on a scale from 1 to 6. As you can see, we gathered similar results for all of the included risk targets. This indicates that overall CO2-based fuels are perceived to rather not be risky for the climate, plant and animal life, or people's health when compared to conventionally used fuels. Moving on, let us have a look at the acceptance of CO2-based fuels. Coming back to this illustration, we see that acceptance is the final factor in the model. There are indirect relationships between the factors we just look at, that means cognitive and affective evaluations. This is because they influence a person's attitude, which is linked to their intention to accept, which ultimately leads to the actual action of acceptance. First of all, again, how do we measure acceptance? In this study, we used 8 different statements, or so-called items, that articulate some form of support or willingness to use a product or technology. For each of these statements, people again indicate how much they agree or disagree to each statement by clicking the according box. In this particular survey, we showed the 8 statements separately to respondents for both road traffic and for aviation. Afterwards, we combine the mean agreements of the 8 statements into one variable. In this case, for both road traffic and aviation, this allowed us to build to the variable acceptance of CO2-based fuels. Afterwards, this allows us to check the acceptance of CO2-based fuels separately for road traffic and for the aviation sector. As can be seen in the figure on this slide, there was no significant difference between these two. On a scale from 1 to 6, the mean value for acceptance in road traffic is 4.22, while for aviation it is 4.27. Although there was no significant difference, we can conclude that people tend toward acceptance of CO2-based fuels in both usage scenarios, as the mean value for the whole group of people tends toward the upper bound of the scale and therefore to higher levels of acceptance. Finally, let's talk about the relationship between acceptance and the perceived harmfulness of CO2-based fuels. To investigate the connection between acceptance and the perceived harmfulness of CO2-based fuels, we used correlations. First, we correlated the two variables acceptance of CO2-based fuels for the road traffic and for the aviation scenario with people's affective evaluation. The two pairs we used from the semantic differential are the pairs harmful, not harmful, and toxic, non-toxic. For both road traffic and aviation, we identified moderately strong, significant negative correlations. That means, for example, the more a person accepts CO2-based fuels, the less they feel that the fuel is harmful, and the more they think CO2-based fuel is harmful, the less they will accept it. After that, we had a look at the cognitive evaluation and its relationship with acceptance. As an example, we depicted 2 risk targets on this slide. one's own health and the climate. Correlations again showed that there are strong, significant negative connections between a person's acceptance and their risk perception. That means, for example, the more a person accepts CO2-based fuel, the less they fear negative consequences for their own health and the climate, and the more they fear these negative consequences, the less they will accept CO2-based fuel. Let's summarize what we've just learned. Acceptance can be influenced by a broad range of factors. We have had an exemplary look at two of them, affective and cognitive evaluations of a product. In the case of CO2-based fuels, we find that they are perceived as less harmful, less toxic, less risky, less dangerous, less polluting or dirty than conventionally used fuels. For the risk targets that were included in this study, no elevated risk perceptions for negative impacts were identified. There were no significant differences between acceptance of CO2-based fuels for their use in road traffic and for their use in aviation. And finally, there is a connection between the acceptance of CO2-based fuels and people's affective and cognitive evaluations of this type of fuel. This brings us to the end of this video. Here you see the used references from this video. Thank you for watching this video. You can find more information on the project on our website or on social media, on Twitter, LinkedIn and YouTube. Thank you and have a nice day.